Welcome to our help video giving the instructions for how to complete the 5-3 Introduction to Trends on the Periodic Table of Elements. Specifically in 5-3 we are going to do a discovery lesson which involves a simulation on atomic radius, ionic radius, and ionization energy. So when you look on 5-3, you'll be able to click on the video lab. And the first part of this lab right here, it's really an investigation, a discovery approach to learning about the periodic trends on the periodic table of elements. But in this discovery lesson, the first page is just gathering the background information. So you'll click on the background vocabulary for the lab because there's some terms that you'll be doing in this simulation that we need to get familiar with. So click on that little link there and fill in these blanks, which are copied straight from the information. So when you open this background vocabulary for lab, you'll see these exact paragraphs on that site. Just fill in the blanks there. Then you need to get a definition for atomic radius, since this lab involves atomic radius. And then you'll need a definition for ionization energy. So click on those two. This is completion, atomic radius is, and when you click on definition, it'll complete that for you. Click on definition for ionization energy, and you'll complete the definition for ionization energy by starting at the blank and adding everything after that. And then they give you an equation for ionization energy. Look at that equation and fill in what is missing on that equation in the gray box. Then once we have the background information, it is time to start the lab. So we'll click on the link taking us to the lab. There we go. And we are now there. This is the periodic table that you'll be using as we investigate trends, which are patterns on the periodic table regarding atomic radius. When we look at our actual lab report, in the very first table, they want us to fill in the atomic radius and ionization energy. And on this first part, we're going to be looking left to right through a horizontal row, which is called a period on the periodic table of elements. It's also called a shell and energy level. So on that first period, we have hydrogen and helium. So we're going to click right here, and we want to compare hydrogen to helium. They are on the first row. So I'll click on hydrogen, and I'll click on helium. And right down here, they'll compare them. Here's a diagram, a Bohr diagram of hydrogen. It has one electron, and that one means one proton. Helium has two protons and two electrons, as it says right up here. We look underneath, and it gives us the ionization energy, which we'll know what that means here after you do part one, and it gives the radius. You can copy and paste these ionization energies and atomic radius right back on our chart. Notice, though, that this has atomic radii on top, ionization energy on the bottom, whereas in the actual lab simulation, they have ionization on top, atomic radius on the bottom. So make sure you get them in the right order on our table. We didn't do that to be difficult. We just did it because we're going to look at atomic radius first and ionization energy second because of how they relate to one another. One of those causes the other trend. So that's why we have atomic radius first, ionization energy second on the chart. After you have those two, we're going to go to the second row of the periodic table of elements called the second period. We're going to look at lithium and carbon first. So how do I get to lithium and carbon? I've got a reset on the reset button, that little arrow, and I'm going to click on lithium. It looks like we're not worried about beryllium and boron, but we are worried about carbon. So we're going to compare lithium and carbon. There they are. You're going to transfer the information. You can just copy and paste these things right onto the table. After we do lithium and carbon in the second row, we're then going to reset right here. And then we are going to be taking a look at oxygen and neon. We're not doing them all. We're going to do oxygen and neon next. And we will write that down. Now, when you do all four of those, So on the second period, we've done lithium, carbon, oxygen, and neon. And we want to see, is there a trend? So as we end up filling out all these periods, you're going to be looking at the numbers. What happened to the atomic radius as we go left to right through the period, row, energy level, or shell, and what happens to ionization energy? And we want to look at the 6 periods that they have information for on their table. So when we look on their periodic table of elements, if they're green, well, the black is the ones you're actually comparing at that time. If they're green, they have data. If they're white squares, they have no data. But we can get all the data we need from just looking at these. The ones that they gave us will be enough to show us the trends. So once we have this entire table filled out, and it might be a little bit repetitive to have to do all these, but the very act of copying and pasting these will enable you to better remember what the trends are. The very act of pasting them in there. When we're done doing that, they're going to ask what happens to the atomic radii, left to right, horizontally, across the row. What happened in row 1, row 2, row 3, row 4, row 5, row 6. Then they're going to ask you what happens to the ionization energy across each of those horizontal rows. And then they have a summary question. Then we're going to look for trends vertically, top to bottom, through a column, which we call groups or families. So then we're going to compare hydrogen, lithium, potassium, and cesium, clicking them on there. Now, if it saves you time, if you have the information already on this table, you can copy and paste it from this table right onto this table. Many of them are on both tables, and that will save you time as you do the lab. But when we're done posting all those numbers, we want to look to see, is there a trend or a pattern top to bottom with regards to atomic radius and ionization energy. Here, ionization energy was abbreviated IE because it wouldn't fit in the square. Once you've done that, they're going to ask you, did you see a pattern for atomic radius top to bottom? Did you see a pattern for ionization energy top to bottom? What was that pattern? You're going to summarize it on this question. Then we're going to look to see what happens to the size of an atom when we remove electrons from it. Ionization energy is the energy it takes to remove the electron, but what happens to the size of the atom? How do we do that on their little table? All right, let's reset it. The reset button's right here, and let's just look at beryllium. Let's make sure we didn't, oh yeah, beryllium's not on there. So let's look at beryllium. I punched up beryllium. First ionization energy of beryllium is 898. Its atomic radius is 112. First ionization energy is the energy it takes to remove the first electron. So let's remove an electron from it. How do we do it? We click on the electron and we drag it off. And then you have to click that I dragged it off. Now it didn't tell us what happened to it. It didn't say what happened to the radius. Did it get smaller or bigger? What's the new radius? Why? Because it says it's not stable, which means we need to remove another one. And it would make sense. See, we had one here. We had 2. But that second level takes 8 electrons to fill it. So what's easier for beryllium? To gain 6 electrons and become 6 minus, or to lose 2 electrons and become 2 plus? So there's the second electron. I'm pulling it off. Well, it looks like we wanted to make it 2 plus because now it is stable, and they gave us the radius of the ion right down here. The radius of the ion is 45. So it started at 112 and now it is 45. And when we removed the 2 electrons, it left the inner level full. That inner level only holds 2. The first level only holds 2, so it satisfied the duet rule by removing those 2. But now I know what the radius is. So on the table, you're supposed to do what happens to sodium when you made it 1 plus, what happens to strontium size when you made it 2 plus, what's aluminum's radius, the ionic radius when you made it 3 plus. It's going to tell you what happened when you remove the first electron from strontium. In other words, did it give you an ionic radius after you remove the first electron? Or did it say something different? Then they want you to click on oxygen and see if you can remove electrons. How will we do that? Boom. Now we click on oxygen. You can only click, you're allowed to click on one element. You don't always have to compare two. So I've got oxygen right here. I pick one of them and I'm going to try to remove electrons from it. See if it'll let you do it. And if it won't let you do it, why won't it let you do it? That's the question they're asking. And then finally, this simulation, this discovery using this periodic table of elements will represent atomic radius on a graph. How do we get the graph? Well, let's first of all click on a couple elements there. We've got oxygen. Let's compare it to chlorine. And now we want to see the graph of atomic radius. Come down here where it says go to graphs. Click on go to graphs. The screen turns white. You're like, oh my gosh, something's happened. It's not working anymore. Well, they just put the graph up here. This is the atomic radius. Here's oxygen's atomic radius right down there. And it puts a line through it. It's 48. Here's chlorine, who's on a whole row underneath oxygen, and it's to the right. Its radius is 79. But on the graph that we're looking at right here that you're going to compare, this is the atomic radius of every one of the elements that we have on the periodic table. There's hydrogen, there's helium, there's lithium. It has them all on there. And you can see the trend on that. To help you see the trend, though, some lines were added. Here's the trend for the group with lithium. That's the second group on the periodic table of elements. So I'm closing the graph so I can get back to the periodic table of elements. Lithium through neon is the second period on the periodic table of elements. There's a line connecting those. Then this has helium. Oh, I'm sorry. That's the, hold on. Lithium, sodium, potassium, rubidium, cesium. That's not the second period. That is group one. We're going this way. Lithium, sodium, potassium, rubidium, cesium. That's group one. Then there's a line connecting group 18, which we call family Roman 8, right here on the chart. So there's lines connecting these. These are group numbers right here. Here's the line is going slightly upward from lithium to cesium. The line's going upward from helium to xenon. Why is the line going upwards through that group? Now there's lines connecting the periods or horizontal rows. Lithium to neon is the second period. Sodium to argon is the third period. Here's sodium, argon, that's the third period. There's lines connecting those, and those period lines are going down. Explain why the slope of that graph is going down. And it also looks at ionization energies. So we come back to this thing. Let's look at ionization energies. How do I do that? Click go to graph. The graph appears up here. There's the graph, but this is the graph of atomic radius. I want the graph of ionization energy. So I come down. First ionization energy from all of those. Click on it. This is the ionization energy graph of all the elements. That graph is right here, already copied for you. All the elements. There's a line connecting helium from xenon. There's a line connecting lithium through cesium. Those are groups. The group lines go down. Explain why. Here's some lines going up, connecting the horizontal rows, which we call periods. Those lines are going up. Why is the line going up, sloped upward? Explain. And then finally, how do they actually know what the atomic radius is of atoms? How can they find that? Click on this and it'll tell you how they can find the atomic radii, something so small. Now you don't have to understand it, but just click and tell me how they do it. And then how did they find ionization energy? Click on that link, fill in the blanks of information provided on that link, and you'll be explaining how they find ionization energy. This is a great discovery lab. This is huge because everything we look at this year depends on your understanding of this topic. Good luck.